Now for the second problem here, 3.42, we need to identify the reagent that will be required to react with the hydrocarbon to give the following compounds as products. Alright, so let's take the simplest example first, and that should help us understand what we need to do for the other ones. So this problem has 1, 2, 3, 4, a 4 carbon chain. So 2, 3, 4. On the second and third carbon, you have 2 bromines, and the rest are hydrogens. Right. Now we can see that there are 2 bromines on the 1,2 carbon atom. Like, if this is carbon atom 1, that's a carbon atom 2. So when there's a 1,2 dibromo, you just need to recognize that there was the reactant should have a carbon-carbon double bond, and then the Br2 adds to the carbon-carbon double bond, like we saw in the earlier case. So you can either take the trans alkene or the cis alkene, it doesn't make a difference in this specific case, and react that with Br2, and that's pretty much the answer to that question. If we had given a cis alkene as a reactant and reacted that with Br2, you are still going to get the same product structure. Now problem B, we have to first make sure we write this product structure in an expanded form. So always make sure you know how it looks in the expanded skeletal structure, so that you can identify which carbon has what group. So this is a CH3 twice, so that means you have a CH3 here, and then you have CH3, and that is connected to a CH. That's connected to a CH. And that CH also has an OSO3H. So you need to know what this group is. OSO3H is an oxygen connected to a sulfur connected to H. So that is the OS123O3H. So this is the counter anion of sulfuric acid, because sulfuric acid, which you should know, is this. When added to an aqueous medium, sulfuric acid is going to dissociate to give you H plus and SO4, HSO4 minus, and as I explained in the class, this can have resonance, which is why this is a very stable anion, and that ends up giving you a structure that is very similar or exactly the same as the previous one. Therefore, this level of symmetry and this level of conjugation makes this molecule or this ion very stable, which makes this a very strong acid. But anyway, so when this sulfuric acid dissociates and it attacks an alkene, you end up having a carbocation. So that alkene ends up is in this case going to be this carbon-carbon structure. So if this is the product you're getting, that means that this HSO4 minus anion attacks the carbocation, which is the carbon containing structure here. So the carbocation in this case should have been this carbocation, and the HSO4 minus would have attacked this carbocation to make the product here. That means you should have started with propene and reacted that with sulfuric acid. So sulfuric acid dissociates, it releases H plus. H plus attacks the double bond here, generates this carbocation. Sulfuric acid releases this nucleophile, and that nucleophile ends up making a bond with the carbon here to make the product here. So therefore it's very important for you to know what the expanded structure of this given condensed form is. So always start with writing the expanded form. So again, in this case, you have tertiary butanol. So you have CH3 thrice COH. So you have CH3 thrice, which is 3 CH3s attached to a carbon, and you have an OH. So therefore you have to know, I'm going to just expand this. So always identify where the nucleophile is. So this is a CH3, I'm just writing it as CH2 and H, because this carbon has the nucleophilic part. That means the adjacent carbon, there should be double bond here, and this carbon would have received a hydrogen in the form of an H plus. Therefore, you should be removing these and making a double bond between those two carbons for the reactant. Therefore, this is carbon atom 1, 2 and 3. This is 1, 2 and 3. There's a double bond between carbon 2 and carbon 3, and that should have reacted with H2O. And as I just mentioned, H2O is not strong enough, so you need to add a small amount of acid for this reaction to happen. So this is the reactant, reagent, product. Okay, let's try to answer problem F. So 1, 2, 3, 4, 5. This is a 5 carbon chain. So 2, 3, 4, 5. CH3, CH2, C, Cl. 1, 2, 3. There is a chlorine here, and then another chlorine there, and CCl2, 2 chlorines here as well, and CH3. Alright, so if you want to get this as a product, let's first see what the precursor is going to be. So obviously you should have reacted this with 2 chlorines. So you have Cl2. So if this is what the first chlorine that you add on one carbon, and this is the other chlorine you add on the other carbon, that means you should have a double bond between these two. Therefore, keep a double bond. But then these are not hydrogens, these are chlorines as well. So this is the alkene you would start with. When you react this dichloroalkene with Cl2, you will get the product. Now, as the problem says, you have to start with a hydrocarbon, which means you would start with an alkyne, because alkyne, so 1, 2, 3, 1, 2, 3, triple bond 1. Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's a 5 carbon chain. So if you first react this alkyne with Cl2, it gives you the dichloroalkene, and further reacting the dichloroalkene with another molecule of Cl2 gives you the product here, which means the right answer, to succinctly express the answer, you just need to take this corresponding alkene and react that with 2 equivalents of chlorine molecule to get this product. Alright, so let's answer question H. So here you have a cyclohexane. So this is cyclohexane 1, 2, 3, 4, 5, 6. So you have a cyclohexane. I'm going to draw the product structure now. And then you have a methyl group, and you also have an OH here. That's an OH, that's the oxygen, that's a hydrogen. Alright, OH here. So if you want to get this, that's the carbon, and that carbon has the nucleophilic OH part. Now there are 3 other carbons attached to this. Now these 2 carbons are the same because they are attached to the same groups on both sides. Therefore it's just enough to look at one of these carbon. So there's a hydrogen there, and this carbon also has a hydrogen there. So if you consider this to be the nucleophilic part of the reagent, and if you remove that hydrogen along with the nucleophilic part, right, then you need to have a double bond over there. So that is one alkene, and you should be reacting this with water. And as always, when it's water, just add a small amount of acid as a catalyst. And if you want to remove this hydrogen, that is also a correct answer. Therefore, the second possible reactant to give the same product with the same reagent is going to be that. Take this hydrogen off, take this OH off, and put a double bond between those two. So I'm just going to use that over there. So this is carbon atom A, this is B, and this is a C. This is carbon atom A, both sides are B, and that is carbon C. Okay, so when you take this reactant, treat it with acid and water, the acid is going to go after the double bond here, it should produce a carbocation on that carbon, which is a tertiary, which is more stable, and water adds to that and eliminates a proton to give you the product here. Same story here. H plus adds to the double bond, you get a carbocation on the tertiary carbon. Water acts as a nucleophile, and you get OH2 plus with the carbon oxygen bond, and you remove the H plus to get this product here. So these are both equally correct answer. But if you want to do the synthesis in the lab, let's say for example you choose this over this, because you'll be getting almost 99% of this product as a major product. With if you choose this alkene, you'll be getting this as the minor product, that as the minor product, but it should be about 1%. Just I'm giving you a ballpark range, so don't take this number very seriously. We're just trying to drive the point that this will be the vast major product, this will be a minor product. Whereas in this case, you'll probably get about 85% of tertiary alcohol as the major product, with only about 15% of this as the minor product. So this will be 85 and 15, and the reason, sorry, not this, this as the minor product. So you'll still form a significant amount of the minor product here. You won't form as much minor product here, because if this product has to form, you have to have a secondary carbocation which is fairly stable, though tertiary is more stable. That's why I get this as a major product. Whereas here, primary carbocations are just absolutely unstable. They form in really small quantities, if at all they form. Therefore, you will see far less amount of this product forming when you choose this alkene as the reactant.